Hello, in this video, we're going to be starting on the first section we're going to cover out of chapter 11. Now, chapter 11 deals with systems of equations and systems of inequalities. We're going to restrict our focus to just systems of equations. And in particular, we're going to focus on systems of nonlinear equations and then systems of three linear equations, so very specific types. We will review systems of linear equations just to get you kind of back in the feel of it, because it may have been a while since you've done Algebra 2 and you may not recall it, or perhaps you took intermediate algebra where you learned to solve systems of equations. So let me share my screen with you and we'll get started. Okay, so first thing we want to start with before we talk about nonlinear systems of equations is we want to actually talk about linear systems of equations. So we want to review what a linear system of equations is before we get into the nonlinear. Now, a system of linear equations is basically two lines that are interacting somehow. Now, if you have two lines, there are really only three possible ways they can interact. They cross at one point and one point only, or they're parallel, so they never touch and never cross. And if they're parallel, then they have to have the same slope, but a different y-intercept. So same slope, different y-intercept, parallel, no solution because they never touch or cross. The third possibility is a little bit weird. It's when the lines lie on top of one another. Now, in this case, it's not true that all points work, but all points on the line are obviously on both lines because they are the same line. In that case, they not only have the same slope, they also have the same y-intercept. So both are the same. Now, you may say, well, that would be obvious. Well, not always. Sometimes lines can be written in such a way that unless it is in slope-intercept form, it's very difficult to tell. Now, we'll look at two ways of solving systems of linear equations. This is just review material so that you'll be ready to solve systems of nonlinear. One of the methods we'll use is called substitution, and the other one is called elimination by addition or addition-elimination method. So what does it mean to have a solution to a system? So let's take a look at the system that we have here. We have a system 2x plus y equals 15 and 3x minus y equals 5. We will often put a curved bracket on the left-hand side to indicate that we want to find the point or points that are on both equations at the same time, where they cross, where they touch. In the case of two lines, that's either one point, every point on the line, or none of the points on the line. So we only have three cases. In this particular situation, you can see I've graphed the two lines here. So I've graphed the line 2x plus y equals 15, and this is not in slope-intercept form. And I've graphed it here in red, and then I graphed the other equation in our system of equations, 3x minus y equals 5. And you can see, if you look right here, that they do intersect at the ordered pair 4, 7. Now, what does that mean? That means if I plug in 4 for x and 7 for y in both equations, I'll get a true statement. So you'll see that that's happened right here. So taking the first equation, 2x plus y equals 15, and substituting 4 in place of x and 7 in place of y, I find that 2 times 4 is 8, and 8 plus 7 is 15. So it's a true statement because 15 does equal 15. That's true. Now, if I look at the second equation here, 3x minus y equals 5, and I'm going to substitute 4 for x and 7 for y, I get 12 minus 7, which is 5, which is also a true statement because 5 does equal 5. If I get a true statement in both, then it is a point where those two curves have to cross or intersect or touch. And in the case of lines, if we find one solution, that's the only solution, because other than if they're the same line. If they're the same line, we have infinitely many solutions, but only points on the line. In this case, though, they're clearly not the same line because they're different. The red line has a negative slope and the blue line has a positive slope. If we have a situation where they're the same line, something weird will happen when we try to solve it. And I'm going to work one of those for you just to kind of remind you of what happens. Now let's take a look at solving this algebraically. This is using a graph, which is great as long as your solutions are at integer values and relatively close to the origin so you can find them, but not so great if it's like 4,432 divided by 11, comma, negative 287 divided by 32. That's not so pleasant. You're not going to find that. You're never going to be able to tell me exactly what the solution is by graphing. So we need algebra. So what we're going to do is we're first going to look at the substitution method. And when you use the substitution method, and I will tell you that it is probably the most commonly used method. When we use the substitution method, we look for a variable term with a 1 or a -1 coefficient. Those are the ones that are easiest to solve for. So when we look at the equations over here, which ones would be the easiest to solve for? The y out of the first equation or the y out of the second equation? Those would be the simplest to solve for. Now, I prefer not to have the negative, so I'm going to take equation 1. And I'm going to label my equation so I know which equation it's coming from and which equation it is getting substituted into. So I'm going to write from equation 1, I have y equals 15 minus 2x. Now that came from equation 1, so I must use equation 2. You're required to use both. So now I'm going to substitute for y in equation 2. And my dog has come looking for pets. Hello, Mojo. Substitute for y in equation 2. So equation 2 is 3x minus something, which is the y, equal 5. And I'm going to substitute what I have here from equation 1 into equation 2. Open up parentheses, oops, and drop it right in there. I got a little carried away on my 2. So again, you must open parentheses. That will protect you from missing a negative or remembering to distribute something. Notice here that I do have a negative outside the parentheses, so I apply the distributive property, which gives me 3x minus 15 plus 2x equals 5, right? So when I get this, I need to clean this up and simplify it. The balance point is here at the equals. So I already have 3x and 2x on the same side. Don't move one of them by subtracting because they're already both on the left. Just combine them. So that's using the commutative property where we reorder things. And then it equals 5. So then I can add 15 to both sides. And I'm running out of space, so let me scroll up a little bit. And this will give me 5x equals 20. And then I can divide both sides by 5, and I get the solution that x equals 4. Now, in this case, I wrote 4, I should have been writing divided by 5 equals 4. In this case, we don't see the extraneous solutions or false solutions that we saw in the logarithm and exponential equations. If you get a solution here, that's it, unless you have made a mistake. Now, x equals 4 is only the x coordinate of where they cross. Now I need to find the y coordinate. The substitution method is ideal for this because you've already substituted for y, which means you've already solved for y. So let's take this equation here, highlighted in yellow, and we'll substitute in x equal 4. So now substitute x equal 4 in y equal 15 minus 2x, which came from equation 1. So this will give me y equals 15 minus 2 times 4, which gives me 8. So I have 15 minus 8, which gives me 7. These are not listed separately. This represents one ordered pair, one point on the graph. So we'll give our solution in ordered pair form, which is 4, 7. Notice that we only got one x value and one y value, which belong together as one ordered pair. This must be the case that we have two lines that are not the same crossing at a single point. If we had the same line, what would happen, we'll see this later, what would happen is that when I tried to solve this equation that you see here that I've highlighted in blue, all the variable terms would drop out, but I would still be left with a true statement. So it would say 2 equal 2 or 0 equals 0 or 5 equal 5, which is true. In that case, then I know that they had to have had the same slope and same y-intercept, and that's why every variable term dropped out, but I still got it true because the y-intercepts were equal. In that case, your solution is all ordered pairs on either line because really they're the same line. And I'll show you how you can verify that that is the case, that they're the same. Now let's move on and talk a little bit about consistent systems, inconsistent systems, independent systems, and dependent systems. Now, it doesn't actually say in the textbook, so we should probably make that clear. An independent system is when you have only one solution. It is consistent, so it's a consistent system because there's at least one solution. So anytime there's at least one solution, we say it's consistent. So a dependent system is when they turn out to be the same line. So this is also a consistent system because there is, in fact, infinitely many solutions, and it's not really showing up very well. So I'm going to kind of highlight it here. What you have in this situation is you have two lines which are sitting one on top of the other. So when you have a dependent system, the lines depend on each other because they're identical. They're dependent. They're not independent of each other. They don't get to slope differently and go through different y-intercepts. They depend on each other. So it's dependent because they're the same line, but it's consistent because there's a solution. The case where they cross once and only once, which is by far the most common situation, there's only one solution, which in this problem is the ordered pair 7/5, -11/5. It is an independent system because these are not the same line, and it is also considered consistent. Now, if we look at the middle pair, this is the one where the lines are parallel. They have the same slope. They're both slope, I don't know, 4. But they have different y-intercepts. So if we look at this graph right here, you can see that this one's going through -1, and this one up here is going through 3. So they have different y-intercepts. B equals -1 on the red line, B equals 3 on the blue line. But their slopes are identical. This goes up to right 1, up to right 1, and the blue goes up to right 1, up to right 1. Same slope, different y-intercept. How would we know by looking at the equation? Well, the blue line has a slope of 2, but it crosses at 3. The red line also has a slope of 2, but it crosses at -1. In slope-intercept form, that y equals mx plus b form, I cannot hide from you what the situation is. So a lot of students are like, oh, I'm going there first. I don't care what she gives me. I'm going to solve the line for y. Because in that situation, you'll see that the slopes are in fact identically 2, but the y-intercepts are different. Then you know there's no solution. It's an inconsistent system. It is independent because they are not the same line, but it is inconsistent. There's no answer, okay? Now let's take a look over here at the red and blue, and let me see if I can come up with some equations that don't look the same, but are in fact the same line in slope-intercept form. So I'm going to pause the video while I work it out, then I'll turn it back on to show it to you. Okay, I've worked it out, I'm ready to go. So what I did was I wrote the equation of two different lines that don't look anything alike. The one in blue is y equal 2x, which is pretty straightforward. I mean, if you look at the blue, it goes through the origin, so the y-intercept is 0. It goes up to right 1, up to right 1. So that is the equation of the blue line. The equation of the red line is 2y minus 2 equals 4 times x minus 1/2. And you may go, well, gosh, that doesn't look anything like the blue line equation. It doesn't, but it's the same line. How will I know this is the same line? The only way to know it's the same line is to go to slope-intercept form or to graph it by graphing points. What I'm going to do is I'm going to change colors. So, well, let's see, I don't want that color. Let's go gray. So this is going to give me 2y minus 2, distribute the 4, so I get 4x minus 2. Negative 1/2 times 4 gives me a negative 2. And then I need to get y by itself. So first I'm going to move the negative 2 by adding 2 to both sides of the equation, which gives me 2y equals, well, I've got negative 2 plus 2, so they cancel. And this gives me y equal to 4x. And again, I want to isolate y to get into slope-intercept form. This is our favorite form for this reason. I can't hide anything there. So then I get y equals 2x. Oh my gosh, they are the same line. They didn't look the same at all, but they are the same, right? And I can do this in all kinds of ways. I can make them look utterly, totally different, but I can't give them to you in slope-intercept form because then it would be obvious. So in this case, the lines are identical. So the solution is all points on the line. So how do you write that? I mean, how many points are on this line? I mean, there's infinitely many. So how do I write that? So the solution to the last one would be the set of all xy. So we use that curly bracket on the left, then a long vertical bar to represent such that, and then we just give the equation of the line, y equals 2x. This says that I'm going to take every ordered pair that is on that line. And if it's on that line, then it's a solution to this system of these two equations. All right, now let's take a look at what happens when you have an inconsistent but independent system of equations. So we know the inconsistent is the one that doesn't have a solution. Consistent means at least one solution. Dependent means same line. So independent, they're not the same line. Consistent, you have at least one solution. Inconsistent, there are no solutions. All right. So when we're looking at this situation, we're given this right here, and we can use substitution again. So if we use substitution, notice I'm going to go ahead and number my problems. So this is problem 1, and this is problem 2. This time, notice that I've got it solved for x in both equations. If x equals 9 minus 2y, and oh wait, the second one's not solved for x. It's x plus 2y equal 13. Rats. If they were both solved for x, I could just set them equal to each other. The first problem solved for x, so I'm going to use equation 1 to substitute for x in equation 2. It's already solved for me. So I was looking for one with a 1 or negative 1 coefficient to do the substitution method. I could have used either of these, but equation 1 already has x isolated, so that's easier. So now I'm going to take and I'm going to write equation 2, which is x something plus 2y equals 13. So I'm going to be replacing my x here with my 9 minus 2y. So that's what's going to go here in the middle. Always use parentheses in order to do your substitution. I cannot emphasize enough how important that is. Many students make sign errors and other kinds of errors because they don't use parentheses. Just open up a hole with parentheses and plug it right in there. Now, I have nothing outside the parentheses, so they can just be dropped. And I get 9 minus 2y plus 2y equals 13. Now, the balance point of the equation is here at the equals. So the minus 2y plus 2y are already on the same side of the equation. So they just cancel out. And I get the equation 9 equals 13, which is not true. That's false. What does this mean? When the variable terms cancel, it means the slopes are the same. If you get a true statement, it means that the y-intercepts are also the same. If you get a false statement, it's because the y-intercepts are different. So our variables disappeared, which means we have the same slope, but we got a false statement. These numbers aren't the same. That means we have different y-intercepts. These must be parallel lines that never touch and never cross. So what do you give for the solution? Well, there is no solution, so we can do it a couple ways. If you draw a 0 with a long diagonal bar through it, it represents the empty set, which is the same thing as doing the curled bracket and don't put anything inside it. It means it's empty. There's no solution. And that's another way to write it as well, is just to write out in words that there's no solution, which I abbreviate SOLN. All right. Now we have not talked about the addition elimination method. So I want to go back up here to our first equation, and I want to solve this system using the addition elimination method. We've used the substitution method twice. Let's now move to addition elimination. So I have this equation right here, and I'm going to copy it and move it down a little bit on the page because I want to start over and I want to use addition elimination. So if I'm using the addition elimination method, or elimination by addition, however you want to call it, some people just call it the elimination method. That works too. It's not generally called the addition method. I don't know why, but I call it addition elimination because you're eliminating by adding. So I've got equation 1 and I've got equation 2. What I'm looking for are two variables that have the same but opposite coefficients. Now, in order to use addition elimination, the format has to be the same. So I've got to have x term, y term, equal sign, constant in both equations. They have to match. Now, does it always have to be x term, then y term, then equal, then constant? No, they just have to be the same. So I could have x term, then equals, then y term, then constant, but they both have to be that, right? So in this case, notice that we have a 1 coefficient on y in the first equation and a -1 coefficient on y in the second equation. If I draw a line and I add those two equations together, I know you're like, why does this even work? It does work. This is going to give me 2x plus 3x, which is 5x, plus y minus y. They cancel. They're eliminated by adding them. They have to have the same constant coefficient with opposite signs. Then they disappear, and I get equals 20, which is what I had over here. This is an even faster method on this particular problem. It's not always faster. It depends on the problem and how it's set up. Then we get x equal 4. Now, that doesn't help me to find the y coordinate. Then I have to take one of the first two equations and find y. Unlike the substitution method, it's not already solved for y like this one was up here. We don't have that expression, so we'll have to use 1 or 2. Either one works. It should be on both lines, so it will satisfy both. So I'm going to use equation 1, which is 2 times 4 plus y equals 15, which is 8 plus y equals 15, subtract 8, and I get y equals 7. Again, remember to write this as an ordered pair. You do get the ordered pair 4, 7. Now, what about on the one that we solved that was an inconsistent system and did not have a solution, right? Which was this one right here. If I were to solve this one by addition elimination, what would that look like? All right, so let me create some space here because I did not create enough space to do this one. So I'm going to start over and I'm going to resolve the problem. And I've got my system of equations here, but notice these formats do not match. I have, oops, I need a different color. Blue is my favorite, in case you can't tell, it's my favorite color. X equals 9 minus 2y, and the other equation is x plus 2y equals 13. The first one is x term, equal sign, constant, y term. The second one is x term, y term, equal sign, constant. Those don't match. It won't work until you get them to match. Does it matter which one you use? No, it doesn't matter which one you use. Since the first one is x equals 9 minus 2y, etc., I'm just going to leave it in that form. So I'm going to have to transform equation 2. So I'm going to leave equation 1 the way it is right now, x equals constant and then y term. And I'm going to take equation 2 and transform it. What I'm going to do is subtract the 2y from both sides so I can get it in exactly the same form as the first equation. I could have done the same thing to the first equation to get it like the second. It doesn't matter. My new equation 2, which if you want to, you could call it, oh, I don't know, 2 prime or 2b. This becomes x equals 13 minus 2y. So now let's use equation 2 prime, x equals 13 minus 2y. Now I have a problem here. If I want to eliminate x, they have the same coefficient, 1, but they also have the same sign. If I look at the y terms, they have the same coefficient 2, but they're both negative. I need one of them to be opposite. So what I'm going to do, just to save a little bit of time, is I'm going to take equation 1 and multiply by a negative 1. So this notation that you see here means equation 1 multiplied through by negative 1. That will give me negative x equals negative 9 plus 2y. And now I'm going to add together, well, we'll call this problem 1 prime. I'm going to add 1 prime and 2 prime, or 1a, 1b, and 2b. Right? X minus x, unfortunately, cancels. 13 minus 9 gives me a 4, and negative 2y plus 2y cancels. But notice I get another false statement. Not the same false statement that I got up here, where I got 9 equals 13. I got 0 equals 4, but it's equally false. And this tells me there is no solution. Okay. Let's move on and talk about a dependent system. In a dependent system, when you solve the system, either using the addition elimination or the substitution method, the variable terms will drop out because the slopes are the same, but you'll get a true statement because the y-intercepts are also the same. So let me create a little bit more space here. I don't think that's going to be enough to do both methods. So I'm going to draw a line down the middle. And on the left, we're going to do, let's do substitution. Now, in this problem, I only have one variable term that is a good choice for substitution. I'm looking for one with a 1 or negative 1 coefficient, something easy to solve for. The only one that's a good choice is the x right there. So I'm going to take equation 1 and I'm going to rewrite it as x equals 2 minus 3y. So I've rewritten equation 1 as x equals 2 minus 3y, and then I'm going to substitute for x in equation 2. Now when I do that, I have equation 2, which is 3 times the x, which I'm substituting, so I open up empty parentheses, plus 9 times y equals 6. And I'm going to substitute this part right here for this part right here. And this becomes 2 minus 3y in parentheses. Now I do have to distribute the 3 across both terms. So this gives me 6 minus 9y plus 9y equals 6. It balances here at the equals. I already have minus 9y and plus 9y on the same side. They cancel and knock each other out. And I'm left with 6 equals 6. But that's true, which means that these are in fact the same line. They don't look like the same line, but they are the same line. And so my solution set is going to be the set of all ordered pairs x, y such that, and just give one of the equations of the line, that they're on that line, right? Now let's look at solving this one by addition elimination. So when I do addition elimination method, I'm looking for a term that I can get the numbers to be the same, hopefully with opposite signs. If they already have opposite signs, that's always a good one to go for. In this case, both x's are positive and both y's are positive. I'm going to have to change the signs. However, I could get the numbers to match if I took on the x variable, if I took equation 1 and multiplied by -3. So I'm going to take and create a new problem 1b by taking -3 times the old equation 1, which is this equation right here. So now I'm going to have -3x, -3 times 3y is -9y, and -3 times 2 will give me -6. I'm not going to do anything to the second equation because now they have matching coefficients with opposite signs. Now, when I add together to eliminate, you can already tell what's going to happen. Both variable terms are going to drop out, which tells me the slopes are the same. Then it depends on whether I have a true statement or a false statement as to whether it is consistent, inconsistent, or dependent. In this case, I get 0. This gives me 0 equals 0, but that's true. And because 0 equals 0, then I know that I have a dependent system. There are many solutions, all the points on the line. Now, how can you tell by looking at these two right here that they're the same line? One thing you can do is put them both into slope-intercept form. So if I were to take equation 1 and put it in slope-intercept form, I would subtract the x first. So I'd get -x plus 2, and then I'd divide by 3, which would give me -1/3 x plus 2/3. If I do the same thing to equation 2, I would get 9y equals -3x plus 6, and then I would divide both sides by 9. So I get y equals, well, I'm going to write this one out so I don't have to do it in my head. I can see it written. So this leads to y equals, well, they're both divisible by 3. So I get -1/3 x plus 2/3, which is the same equation that I got up here is what I got down here. And now I can't hide it from you. They're the same line, right? The other way that you can tell is notice that if you multiplied equation 1 by 3, you get exactly equation 2. If you can multiply both sides by the same constant and get the other one, they're the same line.